last topic of module number 2. There is what is transfer function. We have seen, we have found transfer function from block reduction techniques from signal flow graph. And in first chapter also we have seen a lot of numerical, that is mechanical system, electrical system. For every system we have found what is the transfer function. Now denominator of transfer function. So transfer function sometime is given by TS. Some book they will be calling it HS, capital HS. Some book it will be calling as GS. So do not get confused. Anything can be the symbol as long as it is output by input. It is called as transfer function. So don't get confused by the symbol. Whenever we are having a transfer function, the denominator equation, whatever is there, that equal to 0 is called as a system characteristic equation. And whenever we are finding the roots of that denominator equation in terms of S, that is called as system pole. So these are the frequencies at which system denominator will become 0 or whole transfer function will have infinite amplitude. Samely at the numerator of the transfer function also there will be a polynomial in S, so you can factorize it, and for those values of S you will be finding that the transfer function is giving you amplitude of 0. So roots of the numerator is called as zeros and roots of the denominator is called as pole. Now previous day lecture I think I had made a small mistake. I was talking very fast, but one thing you have to understand. So if you are having pen and paper, just write it down that if you are inserting a pole in the system, so those who are having pen and paper, you can just write it down that if you are inserting a pole in the system, let it be a stable pole only. So let the pole be in the left hand side of S plane, that is left hand side of j omega axis. But if it's a two pole system, suppose 1 by s plus 2 into 1 by s plus 3, let's say 1 by s plus 2 into s plus 3, and we are inserting another pole to the system. So suppose we are inserting another stable pole, fine. So now the transfer function becomes 1 by s plus 2 into s plus 5 into s plus 1, like that. But system stability in that case reduces. So those who are having pen and paper, you can write down two lines that inserting a stable 0 increases the system stability, and increasing even a pole, let it be stable pole, decreases the system stability or relative stability, you can say. So in next chapter, earlier we will see what is the difference between asymptotic stability, what is absolute stability, what is relative stability. So even if we are adding another pole to, so it's a two pole system, let's say transfer function is 1 by s plus 1 into s plus 2. So there are two poles, one is at -1, another is at -2. It's okay. We are inserting another pole to the system. That means we are making it the transfer function as 1 by s plus 1, s plus 2, s plus 5. So 1 by s plus 1, s plus 2 system with two pole will be more stable compared to the system with three poles, that is 1 by s plus 1, s plus 2, s plus 5. So this is one very important thing we will know this time now, and we will prove it while we are doing it root locus. So we will see a two pole system, we will find it's absolutely stable. That means for any gain, so there is another very good concept, system gain, system DC gain, all these concepts we are going to see now. So for any system gain K, okay, it is generally given in the numerator as a constant K. That is called a system gain. So if it's a two pole system, let's say s plus 1, s plus 2, you put any gain from K, okay, let K be infinity, then also you will find that the system is going to be stable. Okay, but whenever you are putting a third pole in the system, that it becomes now 1 by s plus 1, s plus 2, s plus 5, then the stability reduces. For any value of K, the system will not be stable. So we can by using the transfer function. So two lines I'm asking you to write down all this theory, whatever I'm saying. Those who remember it, it's okay. Those who eventually will prove, so you will understand. Let it actually the relative stability of the system. Adding a 0 increases the stability of the system. So this can be asked as a one mark question or short question in your IEA. That is, what is the effect of adding a 0 or inserting a 0 to a system? You have to say that inserting a 0 to a system increases system stability, and inserting a pole to the system decreases the system stability. So with this understanding, we are going for next theory. So there's a PDF, and this is a PDF from MIT, that is the Massachusetts Institute of Technology. So they are also studying this pole zero concept. This PDF I will forward it to you today with the recording of this lecture and with this PPT. Please go through. So what they're saying is, so the same thing is given in the book of M. Gopal, the transfer function. So they are giving transfer function as HS. So don't confuse. For my notation, when I was teaching, I took HS as feedback gain. Okay, but this case they are taking HS as transfer function itself. So we have taken transfer function as TS. Some book M. Gopal they have taken it as GS. This MIT note they are taking it as HS. So there is no standard symbol for transfer function. It can be anything. So the transfer function provides a basis for determining important system response characteristics without solving the complete differential equation. So generally, for any system, we have done the modeling, that is a mechanical system or electrical system. Generally, the system is given in terms of differential equation. So if you are saying the equation of Vt for LCR circuit, so what we write is Vt is equal to L into dit dt plus R into it plus 1 by C into integral of it dt. So it is actually called as an integro differential equation. So generally system, any system, continuous time system is represented by an integro differential equation, and we cannot solve it very easily in time domain. So that's why what is the first thing we do is we convert the differential equation into, we take it to Laplace domain, and after taking it to Laplace domain we try to find out what is the ratio of output by input, ys by xs. Okay, so ys is the output, xs is the input, and that is actually equal to hs. So these are the steps in solution of a continuous time domain signal which is in time domain of t. And after we do that, we find this kind of a transfer function. So this is the transfer function hs. The power of numerator polynomial is m. The power of denominator polynomial is n. And in this case, n is generally greater than m. Okay, so denominator power of s is generally greater than numerator power of s. So this is a perfect kind of a transfer function. What is a perfect or proper transfer function is numerator is polynomial should be less than denominator is polynomial. Certain times we are finding that numerator there is no polynomial, so all this bm and c and all the thing there is equal to 0. That means there is no s at the numerator and only there is a constant, or maybe there is a multiplying factor k. So this thing, so you see here, so hs equal to ns by ds. So ns by ds is called as numerator polynomial by denominator polynomial. So this is another way of representing the transfer function provides a basis for determining important system response characteristics without solving the complete differential equation. Just give me the transfer function, I can tell you what might be its DC gain, what might be its system gain, what might be the poles, what might be the zeros, and what about the system stability. So all these things we can find out without knowing the system equation. What is the system equation? So system equation in differential equation form. This is a transfer function which is given as a polynomial at the numerator and Laplace polynomial at the denominator. So as defined, the transfer function is a rational function in the complex variable s is equal to sigma plus j omega. So s is called as a complex frequency because s is having two parts. One is the real part and another is the imaginary part. Sigma is the real part, omega is the imaginary part. I told you, I've shown you that you can plot this complex poles minus 2 plus minus 3j. So you have to come in the left side on real axis minus 2 units and go above units 2 that and plus 3 and minus to produce a second oscillation if it is a sinusoidal kind of output. So why next is given you the value of sigma plus j is called as a complex frequency. So this transfer function is in a function of s. So it is often convenient to factor the polynomial in the numerator and denominator. So here you are finding that all this numerator polynomial is written as s minus z1, s minus z2, s minus zm. So there are capital M number of roots of the numerator polynomial, and there are capital N number of roots in the denominator polynomial. So what we can say is there are M poles, sorry, M zeros and N poles I will repeat. So ns is having roots number of m, ds denominator is having roots as n. So we can say the system is having n number of poles. That means n number of frequencies. If you input to the system, system amplitude will become infinite. So S is connected externally to the system. That is called as the complex frequency. So these are the frequency values, okay, at which you are finding poles and zeros. So if s is equal to p and suppose this is s minus 3, if you're substituting s is equal to 3, the whole denominator becomes 0. When the denominator becomes 0, hs becomes infinite. Similarly, if you are putting s is equal to zm, suppose this is s minus 5, let's say, if you are putting s is equal to 5, at the time this part becomes 0, the whole numerator becomes 0, the hs, that is the transfer function, becomes 0. On Zm, these are the m values of s for which the hs value will become 0. This is the first thing. So that's why on Z1, Z2, Z3, Z4, zeros, because these are the frequencies. If we substitute in the equation, we will find that hs value becomes 0. And similarly, p1, p2, pn minus 1, pn, these are the values of frequencies, because s minus pn is equal to 0, that means s is equal to pn. This is the characteristic equation. S is called as characteristic and ds is equal to 0. So if s is equal to pn, in that case, the denominator will become 0, or s is equal to p2, also denominator will become 0. So there are n number of points or n number of frequencies, those frequencies in the system. What you will find is the denominator will become 0. If denominator becomes 0, hs will become infinite. So the definition given here, it is often convenient to factor the polynomial of the transfer function in terms of those factors. So you can find out factors by using, so there might be a function for factors, just find it out. So where the numerator and denominator polynomial are ns and ds have the real coefficients defined by the system's differential equation k is equal to b I a n. Okay, so we find it out. So as written in the equation, whatever that root we i's are zeros, whatever equation is equal to 0. So those are the things as poles. Okay, poles are the and zeros for this activity issue. Can you confirm? Can anybody confirm if my slide is visible?
No, sir.
Okay, I'll relaunch it. Just now it is gone off, right? From the beginning it was not visible, or just now it has become invisible? Please confirm if the slide is visible. Okay, thank you,
It's
Abhishek.
visible, sir.
Okay, so these are the rules and zeros of that. Also some given about poles and zeros, so you can just find out. After poles and zeros, we are going for a very important concept of system gain and DC. Okay, so this is a very important of the students. They might be slipping, just skipping the. But you should listen to the sessions when you are logged in. Please listen to the sessions. Now there are two things. One is very important thing. One is the transfer function. One and zeros are properties of transfer function. It's okay, and therefore the differential equation describing the input and output system dynamics together with the gain constant k, they completely characterize the differential equation. They provide the description of the system. If the voice is breaking, I cannot help. You might have to listen to the video recording, because in my end, whatever recording I'm doing, it's from my mobile. So please stay on. Just listen to whatever is visible. If I log out and log in again, it will waste some more time. Hello. Okay, so now we are going to see there are two concepts. One is called as system gain constant K, another is called as DC gain. So these two concepts should not be mixed up, and these concepts you will be requiring whenever you are doing filter design. Okay, so whenever you are designing some filters, maybe you will be in DSP or maybe higher some other subjects. So during filter design, this gain constant and DC gain concept will definitely come. So I will tell you that. So together with the gain constant K, so they completely characterize the differential equation. So whenever I'm giving you a transfer function, then there will be three parts. One is the pole, one is the zero, and another is what is the gain constant. And next lecture onwards, this gain constant K will be always coming in our discussion, because the fourth chapter is all about stability with respect to this gain constant K. And I told you that there is the golden rule of control system, that if you are increasing the gain of the system, at that time system stability decreases. So this is the gain constant K, which value if we increase at certain times, we will find that the system become unstable, or the system can be conditionally stable. Let's say if the K is in between range of 0 to 40, the poles will lie in the left hand side of S plane. And as soon as the K is equal to 40, you will be finding that poles lie on the j omega axis. And if the gain K becomes greater than 40, you will find that the system gain K is shifting to the right side of the S plane, or right side of the j omega axis. That means what is the main important thing you have to understand is depending on the value of K. So very important statement I am launching now. Depending on the value of K, the position of the system poles, it shifts. I will repeat, you can write it down in your book if you want, because this is the basic concepts of root locus, which is the topic of our fourth chapter. So depending on the value of K, whatever is the gain constant of the system, the position of the poles changes. So I told you initially that whenever the system is having a higher energy or higher gain, at that time system becomes unstable. And you have found out that unstable means system pole in the right side of the S plane. That means there is a relationship between K and the position of the system pole. So a very important concept here, that if K value is very less or in a small value, so for every system it depends. It varies, but for some system, let's say k value is small, k value is 1 2 3 4 7 9. Likewise, in that case we'll be finding that the poles are in the left hand side of S prime. Now you are increasing the value of k and poles are shifting towards the j omega axis, because the pole position and the k value, they are related. Okay, so poles are not a fixed quantity for a circuit. Pole values depend on the value of k. If you are increasing the gain at the time, poles shift. So likewise, if you are increasing the value of k, so up to 20, suppose whenever k is 19, the poles are very close to j omega axis. As soon as you, so that is still stable, but stability is less, relative stability is less, but still stable. As soon as you are making, suppose k is equal to 20, what you find is the poles are on the j omega axis. So as soon as the poles are on the j omega axis, they start oscillating with a sustained oscillation. So poles were in the left side of j omega axis, they were oscillating, but their oscillation was damping, it was reducing. We have that characteristic, that poles on the left hand side, then also it will oscillate, that means in the y-axis, then also the system response will oscillate, but it will be a decreasing kind of oscillation. But if the poles are on the j omega axis, so let's say for the value of k is equal to 20, what we will find is system response will be oscillatory and it will be sustained oscillation, because we have seen if there is a pole pair on j omega axis, it produces a sustained oscillation. Now you are increasing the value of k beyond 20. So till k is equal to 0 to 90, the poles were in the left hand side, but poles were shifting towards the j omega axis. K is equal to 20, you are finding the poles are on the j omega axis. And then again, if you are increasing the value of gain k, suppose k is equal to 21, you will find that the poles have just entered the positive side of the S plane, or right side of the S plane. That means system becomes unstable. Further increment in the gain, the poles are too much deep into the right side of the S plane. That means its response is exponentially increasing. सो ये कंट्रोल सिस्टम जो है ये पूरा गेन के का खेल है, एंड गेन के विल कंट्रोल द position of the poles. Okay, so increment will shift the pole from left to right. That means whenever gain is goes from stable to the unstable region. So that is why it is called as ones and zeros. It can completely, the gain k can completely characterize the differential equation and provide the complete description of the system. What is meant a complete description of the system? It is nothing but response of the system in time domain. It is the stability analysis. It is pole and zero. It is characteristic equation. So these are called as system complete description. So you give me a transfer function. Transfer function means there are three things now. Previously we were talking about transfer function means only output upon input. Now we will not talk like that. We will say that it is numerator by denominator, and roots of the numerator are called as zeros, roots of the denominator are called as poles, and it will be multiplied with a factor of gain k. K is nothing but called as a system gain. Okay, so now as we are going in the third chapter, next day we will start it. It will be k, pole and zeros. So these three things will be now our function. Let us see the concept of DC gain. So this is gain k constant. So this is in our hand. Audio amplifier is producing some sound. So sound is the output. What we do is we rotate the knob and we make the sound louder. Okay, that is nothing but k. Whenever we are making the sound louder, this is actually we are increasing the gain of the system. Okay, a car is running with a speed of suppose 40 kilometer per hour, and then we press the pedal accelerator and the car runs faster. That is actually we are increasing the value of gain k. Okay, likewise. So what is gain constant k? Now we have understood. Now what is meant by DC gain? So DC gain is a concept, and DC gain and k, they are not same. Okay, k is called as a gain constant. It is in our control. DC gain also is a function of this k, but let us see what is it. So it's an example one. So four small examples we will do, and with that we'll understand what constant, how to find stability, and all those things. So TS. So again, I'm saying TS. So just now I was saying HS. Now I'm saying TS. It is transfer function. Is equal to 3 into s plus 4 s square plus 2s plus 5. Okay, so this is a transfer function, and k value here is 3. Okay, so this is a multiplicand to the transfer function. Now k value is equal to 3. So s plus 4. So s plus 4 is equal to 0. If you do, you will find s is equal to minus 4. So what is the 0 of the system? 0 is minus 4. And find out the roots of this, a square plus 2s plus 5. So you know how to find it. So this is minus b plus minus root under b square minus 4ac divided by 2a, and this is b square minus 4ac, so b square is 4 minus 20, so it will be root under of minus 18. Okay, so that means it will become j. So minus a plus minus jb, this will be the roots of the denominator. So we can find out the poles here. So poles will be complex poles, minus a plus minus jb, but both the poles will be negative. You can find it out. 0 is also negative. So the whole system, whole transfer function will be negative because pole zeros all are in the left hand side of its plane, and the gain is given by 3. So the k value is given by 3. Now we are going to find what is meant by DC gain. Okay, so DC means we have to make frequency S. So S is called as a complex frequency. So S is equal to sigma plus j omega. We have to substitute S is equal to 0 in the transfer function. What we are trying to do? So DC gain of the system, this is the heading of the slide, and from the system gain, so K is called a system gain or simply gain. I am asking you find what is the DC gain of the system. So while finding DC gain of the system, as DC is having input is equal to 0 or frequency is equal to 0, I'm sorry, in that case substitute S is equal to 0 in this equation. So in transfer function, if you substitute S is equal to 0, whatever you call is called as a system DC gain. That means if you bring a DC to the system, how much amplification will be offered to that DC input by the system. So here if you are substituting S is equal to 0, in that case what we find is 3 into 0 plus 4 divided by 0 plus 0 plus 5. So this will be 12 divided by 5. 12 divided by 5 is equal to 2.4. So system is having DC gain of 2.4. System is having gain of 3. The value is 3. And DC gain you can say given by T0 or H0. That means H at frequency S is equal to 0, or T at frequency S is equal to 0. That is actually given as what is meant by DC gain. Very important concept in filter design, because in filter design we know how much is the system at 0 frequency. So I think you used to find something called as A0, okay, in Fourier analysis. So what is A0? A0 is nothing but what is the DC component of the signal. That means whatever signal is given, so it's a Fourier series, means you are trying to you will be given a kind of suppose a square waveform, a periodic square waveform with a certain frequency, 100 hertz, 200 hertz something, and we ask you represent this square wave by means of a lot of sinusoidal waveforms. So if the square wave is having frequency of 100 hertz, that means what does Fourier series say, that this signal is actually a function of lot of sine and cosine waveform of multiple frequencies. That means if I give you a square waveform of certain amplitude, and let's say it's a 100 hertz square wave, that means this can be represented. So it can, or it can be constituted by lot of sine and cosine waveforms of frequencies 100 hertz, 200 hertz, 300 hertz, 400 hertz up to infinity. So 100, 200, 300, 400, 500, 600, 1000, 10,000, all those things are called as the multiplicated frequency or higher order harmonics of the baseband signal. What is meant by baseband signal? If it is a 100 hertz square wave, that means 100 hertz sine wave and 100 hertz cosine wave are called as a baseband signal. So if you are taking the multiplication of that, that means 100, 200, 300, 400. So 200 hertz sine wave is called as second harmonic. 300 hertz sine cosine is called as third harmonic. 400 is called as fourth harmonic. There is nothing called as a first harmonic. Okay, so first harmonic is called as a baseband signal. So what is Fourier series? Fourier series, I give you a square wave signal and I ask you to represent it by means of a sine and cosine, because sine and cosine is forming a basis function. What is meant by basis function? Basis function is the set of a signal by which you can represent any other signal. Okay, so all this has come out of research, and research has shown that sine and cosine is a basis function, or is a set of basis function by which you can represent almost any of the composite signal of the world. But the signal has to be periodic and continuous, then only you can represent that continuous periodic signal by means of a basis function which is given by sine and cosine. And not necessarily it is sine and cosine, there are a lot of other basis functions also. You can define your own basis function by proper mathematics, because basis function is having a lot of properties to prove, properties to satisfy actually. So if all those properties are satisfied, you can say that it's a basis function. So now I am representing any DC waveform, or sorry, any kind of a periodic waveform, let's say square wave, by means of a basis function sine and cos. And first thing I find is A0, AN and BN. So A0 is the DC component of the signal, AN is the coefficient of the cosine part of the signal, and BN is the coefficients of the sine part of the signal. So if you're adding all this, so, okay, so if you're adding DC, AC, sorry, if you're adding sine, cosine with DC, okay, so that DC is nothing but A0. Okay, so A0 is called as the average DC component of the signal. So that and this thing, not similar, but kind of a same analogy I'm trying to draw. That means you put the system, you just put AC, S is equal to 0, that means AC is equal to 0 frequency, that means DC in the system, and whatever value of TS you find, that is called as the DC gain of the system. That means if you are inputting DC to the system, suppose 2 volt you are inputting to the system, it will be multiplied by 2.4. That means if you are inputting 2 to the system, 2 volt DC, output will be 4.8 volt. This is what is meant by DC gain. That means DC gain is 2. Means inputting 10 volt DC, output from the system you will get as 2.4 into 10, that is 24 volt. So 3 is called as a system gain, and 3 into 4 by 5, that is 12 by 5, that is 2.4, is called as the DC gain of the system. Let us have another example. That is, I will give you another transfer function and I'll ask you what should be the value of K if I want a DC gain to be 12. So for the system requirement, let be a low pass filter. Generally, low pass filter is having DC gain as a very important factor. So I give you a low pass filter and I want that whenever I'm inputting frequency 0, I want the gain of the system to be 12. So what is the system given? System is given the same, but in case of this 3, now I have set as K. Okay, so now system is K, pole is at, you can find out, this will be a imaginary minus A plus minus JB kind of a pole. So there are 2 poles and 0 is at minus 4. So in this case, I want how much will be the value of K so that the system is having DC gain of 12. That means T0 value actually I have given you. So DC gain means Ts at S is equal to 0. So S is a complex frequency, sigma plus j omega. Substitute complex frequency is equal to 0. So whatever Ts you are finding at 0 is called as T0. T0 is equal to 12 is equal to K into, substitute here, all the S is equal to 0. So a very important numerical, very simple concept, but in books, concepts are not given like this. That's why you might not be able to understand at a certain times. Very simple, important concept, but I thought like sharing with you. So these are numericals I've created. So T0 is nothing but whenever this transfer function reaches whatever you call it, there you substitute S is equal to 0. So what is 4K by 5? So that 4K by 5 is equal to 12, because the how much should be the system gain if I wanted. Okay, so that means 4K by 5 is equal to 12. If you just solve it, next step will find K is equal to 5 into 12 by 4. So K is equal to 10. So kind of constraint given on us when you are designing, when you are transferring transfer function, people, I want the transfer function should be perfectly stable. Okay, that means whatever transfer function means whatever poles and all these things we are defining, all the poles should be there in the left hand side. So that can be one constraint. Second constraint can be omega n and zeta. So we omega n and zeta. So omega n can be found out from this 5, zeta can be found out from this 2. So whenever we are doing second order system response, we will find what is meant by undamped natural frequency omega n and what is meant by the damping factor zeta. Actually, value of zeta is less, more unstable, and value of zeta is more. In that case, the system is more stable. So that is another parameter of the system. But more important than that, the gain parameter. So the DC gain. So when the S is equal to 0, at that time, how much the system can give, that we should be able to design. So as it is given, I want the DC gain to be 12. That is substitute here. 12 is equal to K into 0 plus 4 divided by 0 plus 0 plus 5. In that case, if you're solving, TS is K is equal to 15. That means S is equal to 15 into S plus 4 divided by S square plus S plus 15, 5. So if the system gain is 15, here K is called a system gain. But DC gain is that means whatever DC input you are giving to the system, let's say if you are giving 5 volt, you are going to get 5 into 15, that is 75 volt output. Sorry, 5 into 12, that is 60 volt output from the system. So this K is a multiplication with the transfer function, but DC gain is a combined thing out of it. When S is equal to 0, whatever is the value of T, that is called as a DC gain. Important concept, please don't mix up. Now, one very important numerical we can see here. So some differential equation is given, and you are finding that HS for that. So it is given that a pair of complex conjugate poles P1 and P2. So that this is a real pole, because this is a real pole. Sorry, this is a stable pole. This is a complex pole. Real, this is a complex, stable. How do I know this is a stable pole? Because the poles are having two parts, real and imaginary. Real part should be less than 0. So if the real part is negative, means the pole is in the left hand side. So you have to say that this is a pole minus 1 plus minus j, because complex pole uh, so it's possible that there will be one pole to the system, that is minus 1 plus j2. Minus j2 is absent. As it has to happen in terms of conjugate. But you have to see that what is the complex pole. Minus 1 and of this minus 1 plus minus 2j. So some many work is given to you. You'll be finding that this will be producing a undamped frequency of 2 radians per second. Okay, so this is actually giving the frequency. So a single real 0, that is z1 is equal to minus 4, and these two are complex poles and gain factor of 3. Find the differential equation representing the system. So whenever this kind of things are given, first you are supposed to find out the transfer function. So you have to say that transfer function h is equal to k. Now k is 3, s minus z. So z is equal to minus 4. So that is a 0. So numerator will become s minus of minus 4. That will become s plus 4. And denominator will become s minus of minus 1 plus j2 and s minus of minus 1 minus j2. So this is the way you are supposed to write down the poles and zeros in the transfer function. Now if you are just mixing all these things, what you find is it will become s plus 4 divided by s square plus 2s plus 5. So this is equal to ys by xs. Now if you do the cross multiplication, so 3 into s plus 4, 3 is nothing but the system gain, s plus 4 is a 0 polynomial, and s square plus 2s plus 5 polynomial. So this is equal to ys by xs. So this whole thing gets multiplied with ys. So ys into
Sir,
s
you
plus
stopped
2 plus 5
presenting.
is equal to, just give me a minute. Now, is it visible now? Okay. So no matter the transfer function is given or transfer function is not given actually, they have given pole and zero and they are asking you to find out what is the system equation. So P1 and P2 are given as -1 plus minus 2j and 0 is given as -4. So this is S minus Z. This is how the pole is. Substitute Z is equal to -4. So numerator becomes S plus 4. Denominator S minus of P J2. So substitute here in case of P1 -1 plus J2 and here in case of P2 -1 minus J2. So whenever you are just mixing everything, you are finding 3 into S plus 4 divided by S square plus 2S plus 5. This is equal to HS, this is equal to YS plus SS. Now you have to do cross multiplication. That means YS into S square plus 2S plus 5 is equal to XS. XS comes at the denominator. So YS into S plus 2S plus 5 is equal to XS into 3 into S plus 4. Now you have to S square ys. If it is S square ys, you take the inverse Laplace transform. This will become d2y dt2. 2s ys. If you take inverse Laplace transform, this will become 2 dy. 5ys. If you take inverse Laplace, it will become 5yt. Now it is 3s xs. 3s xs. If you are taking inverse Laplace, it will become 3 dx or x can be u. And 3 into 4, 12. Okay, 12 into xt. If you take inverse Laplace, it will become 12 of u. So this is from pole 0, you are coming to the system transfer function. Exactly, in this case, what you are finding is system gain is equal to 3 because it is given system gain is equal to 3. But tell me how much will be the system DC gain. So transfer function, what you have to do is equal to 0 here. So you will find this 3 into 4 4 that is 12 by 5. So DC gain of the system 3 into 4 by 5, that is equal to 2.4. And there is no standard rule that DC gain should be less than system gain, DC gain can be greater than system gain. There is no standard rule. It depends all on the value of poles and zeros. Okay, so if the zero value is very less, let's say zero point 0.2 or something. So this is 3 into 4 divided by zero point 0.2. That means it will become almost 60. Okay, so in that case, the DC gain will increase compared to the system gain. So there's a very important numerical, that is pole and zero are given. From there you are coming back to the system function. So from the transfer function, or not from transfer function actually, from the pole 0 you are coming back to the system function. System function means system differential equation. And this is another thing, that is if I give you a system equation like this, then you are supposed to tell me what is the pole 0 diagram. So such many complex things I can give you. So first job is take the whatever is common you can take from the numerator, and remember one thing, that denominator highest power equation, in denominator highest power, this coefficient should be 1. Always try to keep that. Before finding poles and zeros, always try to make the highest power of s, coefficient of that is equal to 1. So if I had given you 10s cube plus 3s square plus 7s plus 5, divide all this thing numerator by 10. So what 10 पहले बाहर ले लो. So whatever is the highest power of denominator, उसका जो coefficient है, that should be 1. That you do first in all the control system numerical. Then take that 10 outside. So from numerator you are getting 10, from denominator you are getting 3, from denominator you are getting 10. So in that case k will be equal to 0.3 if there was a 10 here, if this was 10s cube. Okay, so always try to make the highest power coefficient as equal to 1, and after that you proceed. So now this 3 is taken out, so numerator is s plus 2. So s minus of minus 2, that means the 0 is at minus 2. So 0 in the left side, that means 0 is stable 0. And this whole thing, if you are finding the factor, so first factor will be s plus 1. S plus 1 means minus 1 is a pole of that, and whatever remaining thing, that is actually s plus 1 plus 2j and s plus 1 minus 2j. Okay, so these are the two poles you are finding. So from here, this is the way you are supposed to plot the pole and 0. So how to plot the 0? So 0 at minus 2, so you are showing a 0 at minus 2. This is s minus 1, so this is a real pole, s is equal to minus 1. So this is cross, cross means is a pole, first pole is at minus 1. And this is another pole, s is equal to minus 1 plus 2j, so this is minus 1 plus 2j. So this one is a pole. So s minus of minus 1 minus j means minus 1 plus 2j is one pole, that is this one, and minus 1 minus 2j is another pole. So s is equal to minus 1 minus 2j, that means this part is below, and s is equal to minus 1 plus 2j, this part is above. So this is a system where we are finding the pole zero plot of a typical third order system. Why third order? Because s is cube. Third order system with one real pole, one complex pole conjugate pair. So there is one real pole and one pair of conjugate poles and a single zero. So you can find out what is the inverse Laplace transform of the Sims. So in Sims you can write this, that is 3s plus 6 denominator s cube plus 3s square plus 7s plus 5. Take the inverse Laplace of that, take it to the plot command, and you can see what will come the plot of the system. Obviously the plot will come to 0 as the time goes by, because all the poles are and zeros are in the left hand side of S plane. So this is another example you can find out. So this is another thing I'm adding with your experiment number 4. Find out the impulse response and step response of this system. So please write down this thing. This is another question I'm asking. So draw this pole zero plot, and you are getting this equation, and from this equation you are supposed to find what is the impulse response and what is the step response of the system. So very important session have been conducted today, though it was a little disrupted, but I will send you the slides, what all things we have done. So first we have come to know officially what is meant by pole and zero, and poles are the roots of the denominator equation, zeros are the roots of numerator equation. Poles actually tells us about stability. If all the poles are in the left hand side of a plane, system is completely stable. And after poles and zeros, we found out what is meant by system gain, that is K, and what is meant by DC gain. So system gain, poles and zero together, they are actually forming the transfer function. And in transfer function, TS, HS, whatever you call it, in that if you put S is equal to 0, then whatever value you get, T0 or H0, that is actually called as the system DC gain. And what is meant by DC gain? If you are passing a DC input to the system, that is which is having frequency 0, at that time whatever is the output you get, that output by this input value is called as a DC gain. And finally what we have done is we have given a pole 0 and K value. So I have given you pole value, 0 value and system gain, and I have asked you to find out the system equation in differential form. So what we have done is we have first found the transfer function, that is equal to ys by xs. Then we have done cross multiplication, and after that we have taken the inverse Laplace transform of that. So this is actually called as the system equation in differential form. And the final numerical, we have got a system transfer function hs or ts, whatever you call it. So first we have taken the k value out from here. So 3 if we take out, this becomes s plus 2, that means s equal to minus 2. This is called as 0, that is the root of numerator polynomial. Then from the denominator equation, if there was any coefficient of the highest power of s, that we are supposed to take first outside. So that will also be 3, whatever we have got. So 3 by e to the, there was a 10 here. There is and whatever. So this real exponentially decreasing kind of graph, and this imaginary roots will use exponentially decreasing sinusoidal. So now if you are mixing exponentially decreasing graph with exponentially decreasing sinusoidal, then how is the response? And then this is a 0. So you can plot this only, just plot a 0, that s plus 2, what kind of response it gives. Okay. And in this system also we can find how much is the DC gain. So DC gain is nothing but, if you're substituting s is equal to 0, you'll be finding this is 6 by 5. So DC gain is equal to 1.2 of the system. And so differential equation given, you can find out transfer function. From there you can plot pole and 0. This is one numerical. And if pole and 0 are given this kind of diagram or value, then you can go back to the system differential equation. So this is both the things are possible: differential equation to poles and 0, or poles and 0 to differential equation. All these things are possible. So with that I declare